Hello and welcome back. Today we're going to be wrapping up the navigation agent and making them actually crawl on the ceiling and everything, as you can see here. Now, this is going to be building off of part 1. This is part 2. And so there'll be a link in the description to part 1 if you need to go refresh on that. I would highly suggest you at least watch the beginning of it because there's a Blackboard kind of demonstration in the beginning that explains everything, and you're going to be pretty lost without it. But as always, all the code can be found in the description. Let's go ahead and get started. Alright, before we dive into code, there's a couple things I wanted to go over that I had to change about the basic enemy navigation agent here, specifically having to do with handling things that I didn't really realize until we actually got into practice that just needed updating. So first off, right here where we do is target reached, we originally just had desired velocity equals vector 3.0. What we did end up needing to do, I realized after a little while, was one, we needed to handle gravity here as well, otherwise we end up just floating through the air if we had a little bit too much velocity left over when the AI decided to stop. And two, we need to check to see if we're too far away from the target position, that is wherever the path was intending to go in the end, then we need to set our target velocity based off of if we want to walk towards that location, just so that we generally stay around the same location even if the AI gets jostled or what have you from physics. And then of course handle gravity. So handle gravity is all of the gravity code that I originally had right here. I just moved down into its own function so that way I could call it here, but I could also call it here without having to duplicate code. And you'll notice the last retrieve path waypoint here, I'm using it instead of the current waypoint because it'll just be whatever waypoint was last used. That being said, I do actually have to set it in ready up here using the getNextWaypoint function, just because if I don't, then the first time it comes through, it generates an error right there. So if you go over to getNextWaypoint, you'll see that if we don't have a path, we just generate a generic one based off our current location, and that's fine just for the first frame of physics. Now, in addition to this, there's a couple other things I did end up changing. Right here, I had to check to see if the last retrieved waypoint path was not the current path 0 waypoint, and I ended up figuring out that that was just causing errors and causing the AI to iterate through the path way too quickly. So I fixed that, and now it's this right here, and all those bugs got sorted out by fixing that. And then down here in the set new target, I did end up having to change up how I'm getting the map to get path. It's not an array of vector 3 like it is in C#. It's actually something called a packed vector 3 array, which is kind of its own thing. It's just a very high memory performance method of having a vector 3 array. And so we just have to call that a different type, and you can iterate through it like any other vector 3 array. Now, in addition to this, I also modified how I'm generating the estimated duration. I double it now. That gives the AI a little bit longer to actually get to where we're going. And then for the current path chance, I actually no longer double it as I was falling off the ceiling way too much. This makes it a little bit more consistent about whether it's staying on the ceiling or not. There's also one other thing over here in the current vector. I do end up setting it to a new vector 3 with the X and Z axis being between -1 and 1 and the y-axis being between 0 and 1. So it's always the vector pointed up, but now it's actually properly random. I realized that last time I did it completely incorrectly, and beyond that, pretty much all the other navigation code is exactly like it was before, so we can go ahead and move on with the rest of the code. Alright, we're going to be starting out with EnemyAIController, as that one has the least amount of changes. And there's nothing too crazy here. We're just going to update the target movement bias, and then we're also going to be changing out the navigation agent for a basic enemy navigation agent, as we no longer need the navigation agent 3D. We can also go ahead and remove the roller ball, as that will now be handled by the navigation agent. Now down here on death function, we're going to be having some slight issues because the roller ball no longer exists, so we're just going to replace it with the navigation agent. And then on the place on mesh function, we got two changes here. Instead of just setting the target position, we're going to be using the set new target function. And then instead of using the get final position function, we're going to be using the target position, as we no longer need to call any function. Target position is just going to be wherever we're going to. Now down here in the process function, there's a couple changes we need to do. Instead of using is navigation finished, we now have the is target reached, and we can go ahead and replace that there and there. Then we can replace where we set the target position with the set new target. And we're going to replace the target underscore position with just target position. And then right down here, we're also going to be replacing that with set new target as well. And we're also going to be replacing that line down there. And that's going to be pretty much it for the enemy AI controller. Like I said, not a lot of changes. We're going to be moving over to Limb.gd, which does have a little bit more changes than the AI controller. We're going to be starting off with a couple private variables. We're going to have a grounded as well as a flying time offset. And then we're also going to have a last waypoint grounded boolean. And let's just move that up next to grounded. Now, what these are going to be used for is making it so that when the AI is in the air, when the limbs aren't able to touch the ground at all, then we want to make the limbs kind of flail in the air. So that way, when we move through the air, we have something actually going on. We don't have that weird effect that we were getting before. And to affect this, we're going to need a boolean first to check to see if we're grounded, and then we're going to use a flying time offset. As the movement of the hands is controlled by the limb placement controller, the limbs are all going to be given their own offset so that the limb placement controller can just keep track of one float variable, and then all of the limbs are just going to use that float variable plus the offset as the driver for the sine waves and the cosine waves in order to make the kind of circular motion that we want to make with our hands and legs. So let's move on down to the physics process where there's a couple new things we need to do. First off, we can just delete that debug extensions, and we can go ahead and check to see if we aren't currently grounded, then we need to go ahead and lerp our current target location to a location generated by a function called generateTargetFlyingPoint, which we don't currently have. And then we're just going to lerp it based off the blend speed multiplied by the delta. We'll make that function in just a second, but let's continue on with the physics process first. So if that's not the case, we can go ahead and just do everything else exactly like we were doing before. Now moving down to the set IK targets, we need to handle this slightly differently as well. As set IK targets handles the actual rotation of the hands or the feet, and for that we don't want them to just be sticking out to the sides like they were before. We want them to actually kind of be pointed in the direction of the limbs when we're not on the ground. So let's go ahead and handle that. And first we're going to be doing an if statement that says if we aren't grounded, then do this code, and if not, just go ahead and do exactly like we were doing before. Now for this code, we're doing something a little bit different. All we're doing is taking the limbs IK container's global position, so that's wherever the hand or the foot should be, and we're lerping it halfway between it and the torso's position, and then we're subtracting it from the actual hand's global position. So what this ends up doing is getting a vector that points from the torso to a position halfway between the torso and the hand. Then we can go ahead and use that plus the limb IK magnet offset to get the actual position that we want to look at, which is just kind of away from the torso. And the reason why we put it halfway between the hand and the torso is so that we don't get a lot of flickering rotations based off of the hands moving around too fast, because they tend to move around fairly quickly. And then for the final function, we're just going to be using the LimbIKContainer.lookat function, just like we did down here, and we're just going to pass in the limb IK container's global position plus that new lookat vector, and then we're just going to be passing it in the y-axis of the chest container, and that's just going to get a nice lookat function for the hands and legs. Now beyond this, there's three new functions that we do need to create that we're going to be using in the limb placement controller, and the first one is going to be right here below initialize step. The other two are going to be down below further. The first one's going to be called place foot hard. And really, I should have named this a limb analogous name, but for now, this will work just fine. And all this function is going to be doing is getting a target limb position, just like an initial curve, and we're just going to be overriding everything and forcing the feet down. We don't want to teleport the feet, but we do want to move them down to wherever that location is. Now, the reason why we're doing this is whenever we jump into the air or whenever we land, we want to put all the feet on the ground at the same time and force them down, kind of overriding everything else. So first off, we're going to get the target data just like we normally would from the get target limb position function, and then we're just going to go ahead and create a new curve. We did all of this before, and this is pretty much exactly like we normally do. Then we're going to go ahead and adjust the control points. That makes sure that the hands and the legs are within the tolerances of what the torso is able to do. And then we're going to set our current lerp value and our currently traveling to true and 0. And that'll go ahead and get everything started. Now down here, just below the adjust control points, there's a couple helper functions that we need to go ahead and do. First off, we need a function for actually setting the grounded state. And we're going to be passing in a new grounded state as well as a new flying offset so that this can update the flying time offset. And this is all going to be called from the limb placement controller. Now, the reason why we actually set it off into this new function is so that if the grounded state is currently equal to true and the new grounded state is equal to false, we need to go ahead and cancel whatever movements we're currently doing before we continue. And then whatever the case, we go ahead and set our grounded state to the new grounded state. And last but not least, we need to create that new function for generate target flying point, and it's going to be returning a vector 3, and this is going to be calling a new function that we're about to go create in the limb placement controller called get target limb flying position. And that's going to be passing in this limb as well as the flying time offset. And that's pretty much it for Limb.gd. We're good to go here. We can go ahead and move on to the limb placement controller. Now the limb placement controller is where most of our work is going to go in. So first off, let's go ahead and get the launch velocity multiplier as well as the max launch velocity. Now these two values are going to be used to actually launch up onto the ceiling or down from the ceiling onto the floor, and these are independent of the jump velocity, as we're kind of defining launch as wanting to transition from floor to ceiling or wall, and jumps are just when it's bouncing bouncing around on the ground or bouncing around on the ceiling, whatever the case may be. Down here at the bottom, we're also going to have two new variables for the flight flail speed and flight flail size. And this is just going to be that speed of rotation and the size of the circle that the hands and legs move in while we're in the air. It's going to be created using sine and cosine for each one of the limbs, and they're going to be moving at this speed, and the circles are going to be at this size. We may end up actually needing to set the size a little bit larger, but for the time being, this value will work just fine. Now, in addition to this, we can go ahead and create a new variable for the current flight time, and it's just going to be of type float. And we're also going to create two new variables down here at the bottom, which are going to be last grounded state, and that's going to be using the BasicEnemyNavigationAgent.gd variable type. And then launch requested is a Boolean. Now, the launch requested is going to be to make sure that under no circumstances do we spam the launch, and also if we are requiring a launch, and more importantly, if placefoot hard has been called on all the limbs, we need to not call any updates on those limbs. We need to go ahead and let the feet place properly before a launch occurs. And that's going to be it here. Down here in the ready function, we do need to go ahead and default the last grounded state to whatever the enemy body.current grounded state is. That's going to be grounded state.none, but we're just going to go ahead and default it here so that if we do end up changing the enemy body's current grounded state default later on, we just go ahead and cascade that change here. Now down here in the physics process, we need to change a couple things. First off, we're going to handle grounded state changes. Now remember, the grounded state is not a Boolean, it's an enum. So we have none, grounded, and on the ceiling or wall. So whenever this changes, we're going to first off set the current flight time to 0 so that way we go ahead and reset everything so that the flailing resets. Then we're also going to check to see if the new grounded state of the enemy body equals none. So that means we're transitioning into the air from either the ceiling or the floor. If so, we need to go ahead and set all limbed grounded states to false, and we need to go ahead and give them a new flight time offset. Now the flight time offset, it really could be anything, but I found that random numbers between 0 and 10 get a good result just to make all of the limbs function randomly, and at the end of the day, it doesn't really matter, and you can set this to whatever you like. Now if that's not the case, so our new grounded state is not in the air, then we need to go ahead and go through all of the limbs, set the grounded state to equal to true, and the limb time offset to 0, just to default it to something. And then we're going to use the placed foot hard function. That's going to force all of the feet down. And last but not least, we go ahead and set the last grounded state in equal to the enemy body current grounded state. Now there's a couple more changes in the physics process. We do need to go ahead and check to see if our current grounded state does not equal grounded state.none, and we are not currently launch requested, then we go ahead and do all of our limb stuff. Now the reason why I inset this launch requested is because just below this if statement, I do have an else for if we are currently in the air, so our grounded state does equal none, then we do want to go ahead and iterate this. And if we put this if statement in here and just said, if we're not currently in the air and we're not currently launch requested, then if we were launch requested, it would go ahead and iterate the flight time. And I don't want that. I just want it to zero out when we're not in the air. So we're just going to inset this if statement and everything should work just fine. That's going to be pretty much it for the physics process. Now we do have a new function that we need to create here, and that's going to be the onLaunchRequested function. This is going to be called from the basic enemy navigation agent. And the first thing we're going to do is say, if we're currently already launch requested, just go ahead and return. We don't need to do anything. If not, we need to go ahead and set it to true. And the first thing we're going to do is force all of the limbs down using the placefoot hard function. And the launch request is going to be fired whenever the AI wants to transition. So we want to place all of the feet down, and then we want to wait. And I found waiting about 1/4 of a second is the best. This goes ahead and lets all the feet transition to being on the ground before it actually launches onto the ceiling. Now it's not always perfect, but the end result does work fairly well. And you can just use the await function with the timeout being a signal. So we can go ahead and create a timer and await its timeout all within this function. Now next up, we can go ahead and get whatever the next waypoint is. So this is wherever we're jumping to, either on the ceiling or on the floor. And we're going to go ahead and create a new vector3, which was going to be called requested velocity. First thing we're going to do is add to it vector3.up multiplied by the global position's distance to the requested velocity multiplied by 0.5. And this is an approximation. What you would really want to do in this situation, if you wanted to be accurate, would be to calculate what the required angle of the launch should be in order to get to the destination. This just kind of approximates an arch to point it upwards a little bit by adding to the target location just the up direction multiplied by some value that is dependent on your distance from that location. And in my case, I found multiplying it by 0.5 just seemed to work out fairly well. You may need to tweak this. Now we need to go ahead and create it from a location to an actual vector. So to do this, we go ahead and subtract it from the enemy body global position. So that gets an angle pointed from this location towards that location. We multiply it by the launch velocity multiplier, and we subtract from it the enemy body linear velocity. This gets the difference between the linear velocity and whatever this vector is. So that way, when we add it to the linear velocity, we kind of cancel out any movement that the enemy body is already doing and just force it in this direction. Now, before we actually do that, we do want to go ahead and limit it. So if the length of it is greater than the max launch velocity, we're just going to normalize it and multiply it by the max launch velocity, so that makes sure that we never have a requested velocity change that is greater than the overall amount of velocity it's even capable of changing. And finally, we can pass this off to the enemy body apply impulse function, which is just going to go ahead and apply that to whatever the linear velocity is, and we can set launch requested to equal to false. Now, besides that, there's a couple more changes that I do want to do. First off, down here in the kickoff velocity, I'm going to change the test target global transform.basis.y to just vector3.up. This way, if you're on the ceiling, it doesn't actually kick you away from the ceiling when it moves. Otherwise, you end up just dropping off the ceiling too much. And then we're going to be changing how we get the target rotation for the actual visuals of the body. And instead of doing it the way we were doing it, we're going to go ahead and use the ground normal from the enemy body. So the basic enemy navigation agent, whatever ceiling or wall you're on, you're just going to get that up vector. And we can go ahead and use it for the looking at function of the chest target container. And we're going to do a little bit of work here to make sure that we don't ever get that error that we get with looking at if it happens to be the exact same vector as the up vector. So we're going to create a new up vector, which is just if we do already have vector3.up, then we're going to set it to back if the absolute value of the last velocity.y is greater than 0.99. Otherwise, we're just going to leave it vector3.up. We can go ahead and set our target rotation to the last velocity, with the up vector being that new constructed up vector. We're going to do something similar right here for the get target limb position, and we're going to just be passing in that up vector right here. And then we're also going to be changing up a couple other locations in this same function. Anywhere that we're using the up direction of the chest transform, we're going to pass in that constructed up vector. We're also going to be doing this in a couple other locations. So anywhere that we have the chest target container.globalTransform.basis.y, we're going to be passing in that up vector. And this is going to make sure that any steps we take are going to be based off of the up vector of where we're supposed to be, not necessarily where the torso is. Now, in addition to this get target limb position function, we're going to be creating a new get target limb flying position, which is going to be very similar to this, but instead of just using a target position, we're actually going to be creating a little circular rotation based off of a float variable. So first off, we're going to go ahead and get our up vector just like we did up there. We're going to set our target position equal to the global position plus the up vector. We're going to add to it our linear velocity multiplied by the velocity counting multiplier, and we're going to multiply that by 0.1 if we're on the feet or 1 if we're on the arms. And this is going to make sure that while the arms and legs are both going to account for the velocity of the body, the legs are going to lag behind a little bit, whereas the arms are going to be out in front of the body when it's flying through the air. This just gets a somewhat more realistic look. We can also go ahead and set our last velocity to the new linear velocity if we're greater than 0.5, just like we did in the previous function. And then we can add to our target position the last velocity multiplied by the body length divided by 2, multiplied by -1 if we're in the feet, or +1 if we're in the arms. That's just going to get your offset on your torso, forward or backwards. We're going to go ahead and get our center point and side angle just like we did before. The center point being wherever the target location for the hips or the shoulders. And then the side angle is just going to be your left or your right offset based off of whether you're the left or the right arm or the left or the right leg. We can go ahead and set our target position equal to center point plus that offset, and we can go ahead and set our limb raycast. And then we can do the whole process again in order to get the lower foot, so the actual hand or the actual foot offset, as that is wider than the upper body's offset. Now, the only thing we really do differently than the previous function is now we go ahead and create our flail offset. Now, the flail offset is a vector 3 in local space with the y-axis, so that's the up and down, being the sine of current flight time plus the flight time offset, which if you remember is passed in from the limb and is random for each limb, so each limb gets a slightly different offset. And then the cosine for the z-axis, and this will get an up and down and a forward and backward that are offset 50% from each other, so that way it goes in a full circle as opposed to just an up and down and forward and backward angular wiggle. And then we just multiply that by the flight flail size, as it will return a value between -1 and 1. And we go ahead and add that to our target position using the global transform.basis of the chest target container multiplied by it to get it in world space based off of wherever the chest target container is just generally looking. Now we can go ahead and set our raycast to look at that target location and force its raycast update. we can go ahead and just say if limb_raycast.is colliding, then target position equals limb_raycast.get collision point. And whatever the case is, we return the target position. The whole reason why we actually do, in fact, do the raycast is so that if we're flailing the limbs and we happen to bump into a wall or another AI or something like that, we kind of want to stop and make sure that the arms don't stick through walls and what have you. And this should resolve that issue. And that's going to be it for all of the code. So now we can go ahead and assign our variables. All of this should stay exactly the same. We're going to leave the chance of up path at 0.3, though you may want to tweak that based off how much you want them to actually transition from the upper to lower. We're also going to be setting up a couple things here. And then the flail speed and size should be just fine. We're going to go ahead and save that. I'm going to set all of these to the defaults in the code before I actually upload this code, but let's go ahead and check to make sure all of that works just fine. We do need to go ahead and set up our signal. So the limb placement controller already has the signal for on launch requested, but do make sure that you set this up. If you don't, just none of this will work and it'll never try to get on the ceiling, and we should be good. Let's go ahead and run the project and see how it looks. All right, after a little bit of testing, I realized that we need to actually set this requested velocity up to maybe multiplied by 2. It just wasn't really getting enough velocity to actually bounce up onto the ceiling. And then we also went ahead and set right here in this function where we use the lookat function, we go ahead and set that if we are currently already equal to that position, we add to it the vector 3.down. The reason for this is if you use lookat function at the same location you are currently at, it throws an error. And this occurred on every prefab the first time. So I ended up just adding vector 3.down to it to make sure it's never at the same location. And this only occurs once, you won't even notice it. So this generally just works out fine. So let's go ahead and test that and see how it looks. All right, and as you can see, we're moving around. They're crawling on the ceiling and transitioning from the ceiling to the floor or vice versa. And this doesn't look too terrible. Obviously, there's some work that could be done, but you can currently shoot them off the ceiling and that works just fine. And the AI moves about and transitions fairly well. They still look a bit dorky. Some work to be done there for sure, but for the time being, this will work just fine. Next week, we're going to be working on making them actually damage the player. They're going to be launching towards the player, damaging them, and then repositioning. So anytime the AI actually damages the player, we want them to retreat and reposition around somewhere. And then the week after, we're going to be working on audio to kind of tie all this together and make this into kind of a finished demo. And then we'll be wrapping up the entire series. But as always, thank you all for watching. I hope you all have a wonderful week. We'll see you all back here next week for the next tutorial.